because we know that the derivative is the slope function, then we should be able to figure out what goes in these blanks. If the derivative of a function at c is positive, in other words, if the slope of the function at c is positive, well, what does it mean to have a positive slope? It means that the rise and the run are both the same sign, right? Either positive or negative. And if we're reading a function from left to right, which we always do, well, most of the time we do, then we would say, well, if we're reading from left to right, then the change in x is positive, so the change in y must be positive as well. In other words, y is getting bigger, and that means that our function is increasing, right? A positive slope means an increasing function. Likewise, a negative slope is a decreasing function. One of the problems students have with calculus is equating the word positive with increasing. They're not the same thing. But a positive derivative means an increasing function. Okay, just don't get don't say that a positive derivative means a positive function, right? That's not the same thing. All right, so anyway, if we know that, then we should be able to analyze functions and easily figure out whether they're increasing or decreasing. So given this function, it's a polynomial function in factored form. We'll find its derivative, and probably the easiest way to do this is the product rule, because I don't want to expand this out. That might take a little bit too much time, although we certainly could, and you could try that if you like. But u prime v is the product rule. The argument x minus 1 doesn't change. The 2 goes in front, and the 2 drops down to a 1. We don't forget the chain rule, but it's okay to forget the chain rule here, because the derivative of x minus 1 is just 1. So this is u prime. V is x plus 3. U prime v plus uv prime. U times v prime. V prime is just 1, because the derivative of x plus 3 is also just 1. Now, we have to ask, when is the function increasing? In other words, when is the derivative positive? And when is the function decreasing? In other words, when is the derivative negative? Well, this is a polynomial function, so it's defined for all values of x, and it's continuous for all values of x. So all we really need to do is find the places where this derivative equals 0. I have a mantra in calculus, and that's, when in doubt, take the derivative and set it equal to 0. And that's what we're going to do when we're trying to find intervals on which the function is increasing and decreasing, because 0 is the potential places where our derivative could stop increasing and start decreasing, or vice versa. These are critical numbers, right? We're looking for critical numbers. So we can distribute here, but I don't want to distribute because I noticed that there's an x minus 1 in the first term, and we have an x minus 1 as a factor in the second term, so I'm going to factor out that x minus 1, and in the first term I'm left with a 2 times x plus 3, and in the second term I'm left with a 1 times x minus 1. Still our derivative, still equal to 0, and now we can distribute the 2 and get 2x plus 6 plus x minus 1 is going to be, 3x plus 5. And I said that very deliberately because this is the second time I've recorded this video. The first time I actually put a minus 5 here. And I'll mention later on how I knew that that was wrong. I didn't catch it until much later on, but I saw something that was very strange. And it's worthwhile to just ask yourself whether your answers make sense so that you can catch those mistakes. More on that in a bit. So this is our derivative. It's equal to 0 when x equals 1. Also when x equals negative 5/3. Those are our critical numbers. Those are the places where our derivative is definitely not positive or negative. So on this number line, I call it my f prime line, I'm going to go ahead and put my critical numbers. I'm going to put 1 over here on the right because it's the bigger of the two, and negative 5/3 on the left because that's the smaller of the two. And I like to put a 0 up here to remind me that when x equals 0, when x equals 1, f prime equals 0. And when x equals negative 5/3, f prime equals 0. And these are values that aren't helping us for increasing and decreasing. They're just the boundaries for increasing and decreasing. So now we move on to some test points. So we are going to test some points like maybe I'll test something over here on the left side like negative 2. Negative 2 is less than negative 5/3. If I try to evaluate f prime of negative 2, I don't care what the number is. I just care about whether it's positive or negative. So negative 2 minus 1 is negative, and negative 6 plus 5 is also negative. So we get a negative times a negative, which is positive. All right. And then we try a test value in this middle interval. I like to test 0 because that's our favorite number to play with. And 0 minus 1 is negative, and 0 plus 5 is positive. So we get negative times a positive, and that's going to give us a negative. And then finally, we'll pick a test value over here, like maybe positive 2. 2 minus 1 is positive. 6 plus 5 is positive. Positive times positive is positive. All right, so we've figured out all the different places where the derivative is positive, all the different places where the derivative is negative. Now we can answer this question. We can say that f is increasing every interval where the derivative is positive. So from negative infinity all the way to negative 5/3. Negative infinity to negative 5/3. Because f prime is greater than 0. And then we could also say f is decreasing on negative 5/3 to 1 because f prime is negative. And then finally, we could say f is increasing again on the interval 1 to infinity. Again, because f prime is positive. And you can lump the two increasing intervals together on the same line if you like, using a union or whatever. All right, nothing too revolutionary there. We probably recognize that from our velocity questions from the last unit, when we're asking when is the particle moving to the left or to the right. That's the same idea. All right, so that leads us to the first derivative test. And this is, again, fairly obvious, I think. When you understand the concepts, this is not very tricky at all. As long as we have a critical number, in other words, a number where the derivative equals 0, like we did up here, or a number where the derivative is undefined, and our function is continuous and differentiable, and it doesn't have to be differentiable at c, but it has to be differentiable everywhere else on that interval, then we can use the first derivative test. And the first derivative test is going to tell us a few different things. First of all, we can say if f prime of x changes from negative to positive at that critical number, let's remember what that means. If f prime changes from negative to positive, then what is f of x doing? It must be changing something, right? It doesn't change from positive to negative, though, or negative to positive. It changes from, well, if f prime is negative, then f is, as we just talked about, decreasing. And if f prime is positive, then f is increasing. So saying that f prime changes from negative to positive at c is the same thing as saying f of x changes from decreasing to increasing at c. Now that's something that we understand, right? We're going down when we're decreasing, we're going up when we're increasing. So this magic point right here where it stops doing one thing and starts doing the other thing, where it changes, well, that's got to be our minimum, right? That is a relative minimum of f of x. Okay? So 9 times out of 10, when you're using the first derivative test, after you find the maximum or minimum, in this case minimum, it'll ask you to justify your answer, and the justification will always be because f prime of x changes from negative to positive at x equals c. Or we might see the opposite reason. F prime of x changes from positive to negative. That would mean that our original function is increasing, and it changes to decreasing. Again, that most important word is talk about how it's changing. We don't necessarily care that the derivative equals 0 at this point. It might not even equal 0 at this point. It could be undefined. That's not enough to verify that we have an extrema. That's just a critical number. So we have to see that changing in order to use the first derivative test. I can't stress it enough. Changes. We've got to see that change in sign of the derivative. And anyway, obviously this is going to be a relative maximum of the function. All right. So those are two scenarios, right? There are two different ways that we can change, right? From negative to positive or from positive to negative, when we're talking about signs. The third scenario is it doesn't change, right? If the derivative stays positive on both sides of the critical number, or if it stays negative on both sides of the critical number, then it doesn't stop doing whatever it was doing, whether it was increasing or decreasing. that function is continuing to do the same thing. So that point is actually nothing, according to the first derivative test. The first derivative test is only for finding relative maxes and mins, and if we don't see that change, then that particular point doesn't concern us. We could go a little further and talk about how it's probably something called a point of inflection, assuming that the function is differentiable, but that's later on. That's the next section. So we won't worry about points of inflection at the moment. So anyway, first derivative test talks about whether the derivative is changing signs, and we know that when the derivative changes signs, we have a relative extrema. All right, so back to our friend f of x is that polynomial function we looked at before. Again, we had that f prime line where one of our critical numbers was -5/3 and another critical number was 1. Those were both where the derivative happened to equal 0 in this case. And we had positive, negative, positive. We had 2 intervals of increase and 1 interval of decrease. All right, so all of that work that we already did allows us to not just talk about intervals of increase and decrease, it also allows us to talk about the relative extrema. So for example, because the derivative is positive, the function is increasing, and because the derivative is negative, the function is decreasing. So this point right here, we can see is a maximum. So we can say f of x reaches a relative maximum of f of -5/3, which is, I don't know, this is going to be 8 over 13, -8 over 3 squared. And then -5/3 plus 3 is -5/3 plus 9/3. -5 plus 9 is 4, so 4/3. So we've got, let's see, -8 times -8 is 64. 64 times 4 is 256. And then 3 times 3 times 3 is 27. And that's the relative maximum. And if it asks us to justify it, we would always say, because f prime changes from, in this case, positive to negative at x equals -5/3. All right? And then the other place where the first derivative changes is at x equals 1, where the derivative changes from negative to positive, so the function changes from decreasing to increasing, so that's got to be our relative minimum. So same idea, f of x reaches a relative minimum of f of 1 equals, well, that's easier, that's going to equal 0, because f prime changes from negative to positive at x equals 1. Now, the first time I did this problem and I had an accidental positive 5/3 here instead, I got kind of confused because I found that my minimum was bigger than my maximum. I had a decreasing function that went from 0 to a positive number, and I found that to be a bit impossible. So that's when I went back and double-checked my math, and I realized that I messed up on a negative. So always double-check to make sure your answer makes sense. If I'm at 0 and then if I'm at x equals 1, y equals 0, and my function apparently is supposed to be decreasing, but then I end up finding that it isn't, then I've found some sort of contradiction. So always make sure that your answers are making sense. Learn from your mistakes, or my mistakes. Learn from everyone's mistakes.